So, in this class we will discuss about the reciprocal lattice. As I mentioned, the diffraction spot, basically if I tell Lau spot. So, on a photographic plate, so they shows the symmetry of the crystal. So, these Lau spots are on the photographic plate. This they are, if we look, they have some symmetry as is similar type of arrangement of Lau spot to the direct lattice. In case of direct lattice, whatever the lattice point are arranged. So, in photographic plate, the Lau spots are also arranged with some order. Okay. And each point is basically considered as a point for a plane. So, planes of real crystal are converted into points on diffraction space. So, that is basically is called the K space also, that I will discuss later on. So, so that space where we can think of similar type of lattice as we have seen space lattice. So, in diffraction space also there, so that's we can get that type of arrangement of points where each point will represent the plane of crystal. So, that planes or that lattice is basically called reciprocal lattice. So, why it is called reciprocal lattice and how it is important, that basically we will discuss in this class. So, so we have say A1, A2, A3 axis in space lattice or Brevis lattice or in real crystal. Okay. So, earlier I used A, B, C, but now I am using them as a A1, A2, A3, because I have to set another axis system. So, this A1, A2, A3 in space lattice, they are, if it is this A1, this is A2 and this is A3 in space lattice. So, they will form a unit cell. So, I need space. So, these two has to be parallel. It's more or less okay. Yeah, so this more or less it is done, but it is not perfect one anyway. So, this is the unit cell, this may be triclinic unit cell. So, here this if I define another set of axis, say B1, B2, B3. Okay. So, this definition, if it is like that, the B1, let me write B3 first. B3 equal to A cross A1 cross A2, A1 cross A2 by volume of this unit cell. Okay. So, what does it mean? What is the relation between this this A1, A2, A3 axis and B1, B2, B3 axis? If we define the axis relation between this axis like this. Okay. So, you can see this B3 is so what is A1, A2? A1 cross A2. So, this is the area, of this plane, right. So, this is the area of this plane, this represent area. Okay. I think this is basically area. Okay. Now, what is the volume then? So, if it is area and this direction of this will be that B3 direction. So, it will be normal, B3 will be normal to A1 and A2, right, because this A cross A1 cross B2. So, the direction will be the normal to this plane. Okay. So, if B3 is equal to this, then this B3 direction will be normal to this plane. So, let us draw the normal to this plane. Okay. So, this is the normal, this is the direction of B3. So, this is B3 direction, right. So, from the definition we can get the direction of B3, and what is the magnitude of this B3, that let us check. So, what is volume? Volume is basically V equal to uh, V equal to, I can write this area into height, that will be the volume of this unit cell, right. Area of this one into multiplied with this height, so that will be the volume. So, just here we are writing this area of what I can define, say if it is O, it is A, it is B and it is C. Okay. So, area of OABC, area of OBC, area of OABC, right, into height of this unit cell, right. So, what will be the height of the unit cell? So, this so the height of the unit cell will be, if we just take this projection of this A3 on this normal, okay. So, that will be the height, So, this height, if it is say P, so height will be OP. So, area into height OP, right. So, B3 is basically, you can write B3 equal to, or magnitude of B3 will be, so this area of OABC divided by area of OABC into OP, right. Height is OP into OP. So, you are getting basically this one equal to 1 by OP, right. You are getting 1 by OP. So, what is OP? OP is basically height of this unit cell, and it is also basically normal to this plane OABC, and it is along the B3 direction. So, this direction, this is basically height of which plane? If you see this is the plane, this is the parallel plane of this one, this is the parallel plane of this one, right. So, which plane it is? It is if 001 plane, right. 001 plane. This is 001 plane, and this height, the 001 plane, and this height whatever, this is nothing but the spacing between these spacing between these two planes, right. So, distance between these two planes, right. So, that is nothing but the planar distance. So, this OP is basically planar distance of 001 plane. So, this is one plane and distance from this plane to this plane, they are parallel planes. So, that is the lattice spacing basically. So, this OP is nothing but its planar spacing of 0 0 1 right. So, B3 I got its magnitude of B3 is got this D 0 1 1. So, similarly you can show that in case of B1 in case of say B2, so that will be the planar spacing, that magnitude will be planar spacing of this parallel to this cut this B axis. So, which one, this is A axis, these two A axis, and B axis will be this, okay, it is this plane, okay, and another plane is this. So, that will be distance between these two planes. So, same way you can write D 0 1 0 and B1 will be 1 by D 1 0 0, right. So, just we have derived one from here, the same way one can see that is the magnitude of B1 B2 B3, okay. So, we defined vectors this 3 axis like this. So, this will be A3 cross A1 by volume, right, and other one will be A1 B1 will be equal to A2 cross A3 by volume, right. So, A1, A2, A3, this is the axis for real crystal for space lattice, right. So, now I defined 3 more axes B1, B2, B3 taking this definition, right. So, if I take this definition, then what I see that the magnitude of this B1, B2, B3 is nothing but the reciprocal of the planar spacing, right. So, these 3 axes, it is basically reciprocal of some planar spacing. So, now using this B1, B2, B3, using this axis, if we produce points, lattice points, okay, then it will form a lattice. If we produce many points in points, so it will form a lattice. So, that lattice is basically called the reciprocal lattice, right. Taking this A1, A2, A3, these 3 axes, we can just using translational vector, right, we can produce points in space. Okay. So, they are lattice point of space lattice, right. So, what translation vector we use? So, T equal to UA1 plus VA2 plus WA3, right. So, earlier I used A1, A, B, C, now just A1, A2, A3, just I mentioned earlier. So, this using this translation vector we can produce all lattice points, right. Similarly, using this axis we can produce points in space. Okay. So, it will give another lattice, and this that lattice is different from this lattice, and that lattice is called reciprocal lattice, right. So, for this also we need translational type of vector. So, this we tell this is called reciprocal vector. It is not translation vector, but it is similar. It is this reciprocal vector. Say if it is H, then we can write H B1 plus K B2 plus L B3, right, similar to this, right. Here I have considered HKL as a coordinate, right. So, here whatever UVW, so here HKL. So, this HKL is same as the Miller indices. These HKL are the basically HKL are Miller indices. Okay. So, why should I take the this HKL, right. So, we can show that this is nothing but Miller indices. Okay. I can take other say PQ or other coordinate, but that PQR later on we can show that it is nothing but it is Miller indices. So, directly I have written as a Miller, I have used Miller indices. So, you will find out later on. So, but one can guess also that, so from here you are seeing that basically direction is the this B1 direction, B2 direction, B3 direction, it is the directions are, in this case it will be it will not be along the A1 axis, yeah. So, that I cannot say, but if you take orthogonal axis system like cubic, orthodrombic and tetragonal, where these axes are orthogonal, A1, A2, A3 are orthogonal, then we can show that B1, B2, B3 also they are orthogonal, and A1 will be parallel to B1, A2 will be parallel to B2 and A3 will be parallel to B3. Okay. So, this is the reciprocal vector, we tell this reciprocal vector we define like this, where H, K, L are Miller indices. So, not necessary to take directly Miller indices, other parameter also we can take, but ultimately we will see later on that they will be nothing but the Miller indices, right. So, now important fact is that So, from here you can see that B1 is B1 is the direction, B1 direction is perpendicular, this is the perpendicular symbol, right. This is a B1 is perpendicular to this plane. So, on this plane A2 and A3 vectors are there. So, if B1 is perpendicular on this plane, so it is perpendicular to A2 as well as A3, right. So, B1 is perpendicular to A2 and A3, right, A2 and A3, then B2 is perpendicular to on this plane, right. So, it is perpendicular to A1 and A3, right, and B3 is perpendicular to A1 and A2, right. So, these axes are perpendicular to the, these are axes are perpendicular to the so the axis of real crystal, and then we can see that if they are perpendicular, so we can get some relation that B1 dot A1 B1 dot A1 I cannot say, but I can say B1 dot A2 equal to B1 dot product basically is 0, right. Similarly, B2 dot A1 equal to B2 dot A3 equal to 0. B3 dot A1 equal to B3 dot A2 equal to 0, right. So, in general I can say AM dot BN equal to 0 when M is not equal to N, right, when M is not equal to N. So, what about the other one? This when this M and N are same, like B1 A1 dot A1, B2 dot A2, B3 dot A3. So, what about that one? So, this say if I take B3 dot A3, okay. So, what will be that? So B3 is basically B3 is magnitude along this axis, B3 axis, right, and magnitude is what is 1 by d0, sorry, this I did mistake, so it will be 0, B3 will be 0 0 1, yes. So it is B3 magnitude is 1 by d001, 1 by d001 is nothing but OP, right, it is nothing but this OP, magnitude OP, right. And so this, so here I will not this. So basically magnitude of B3 and magnitude of A3, then this cause some angle between these two, right. So if I take the magnitude of B3, that is OP, and now the unit vector along this B3. Now if we take the dot product of this A3 on this unit vector along this direction, so that is basically projection of A3, right, projection of A3 on this. So this dot product is basically this OP, then magnitude of this one and the projection of this. So projection of A3 along this direction. So projection of A3 along this direction, what is that? It is so this projection of this will be basically, I can, so this A3, so this will be OP, okay, so I did mistake. So B3, magnitude of B3 is 1 by OP, so I have erased it, so it's 1 by OP, because OP is this D001, right, D001. So this will be 1 by OP, OP is D001, right. So into the projection of A3 along this direction, that's projection of these 3 along this direction is OP. So this basically equal to 1 by OP into OP, so is equal to 1, okay. So I can write that this B3 dot A3, that is 1. Similarly, one can show A1 dot B1, A2 dot B1, A2 dot B2 will be equal to 1. So this will be equal to 1 when m equal to n. So this is very important relation, and which follows the reciprocal lattice in connection with the space lattice, okay. So here whatever we have done, so we have defined axis system B1, B2, B3, okay. So this is the axis system of reciprocal lattice, okay. Why it is reciprocal, as I defined, because this reciprocal lattice, this axis system are related with the planar spacing of the space lattice, and their relation is inverse, is reciprocal with each other. So that is why it is reciprocal, and relation between the axis system of both, they follows this, and also this translation vector can produce the space lattice, space point. Similarly, this reciprocal vector, this is the reciprocal vector, it can produce the similar lattice, which is basically reciprocal lattice. So, I will stop here. So, I will continue in next class. Thank you for your attention.